In 1952, a woman sitting at a drafting table in a basement office at Columbia University discovered one of the most important geological features on Earth. A 40,000-mile mountain range running through every ocean on the planet, with a rift valley splitting its spine that would prove the continents are moving. She discovered it by hand, with pens and rulers, plotting thousands of sonar readings onto sheets of paper, connecting dots that no one else had thought to connect, seeing a pattern in the raw data that no one else had been trained or willing to see. She had no computer, no satellite imagery, nor three-dimensional modeling software. She had paper, ink, and a mind that could hold the shape of an ocean floor in her head while she built it, one data point at a time, on a drafting table in a room without windows. When she showed her discovery to her colleague, the man whose name would go on the maps beside hers, the man who went to sea while she stayed behind, he looked at her work and told her it was girl talk. He said it looked too much like continental drift, which was considered a crackpot theory at the time. A scientific embarrassment, the kind of idea that could end a career. And he dismissed it. She didn't argue or protest. She did not make a scene or lodge a complaint or appeal to a higher authority. She went back to her drafting table and kept working because she knew she was right and because the data did not care what anyone called it. Her name was Marie Tharp, and she is one of the most important scientists of the 20th century, a woman who fundamentally changed our understanding of the very planet we live on, who revealed that the ocean floor is not a flat, featureless plain of mud, but a dynamic, mountainous, volcanically active landscape, as complex and as dramatic as anything on land, and who provided the critical evidence that finally convinced the scientific community to accept the theory of plate tectonics, the single most important unifying theory in the history of the earth sciences. She did all of this from an office she was not allowed to venture outside of. For the first 2 decades of her career, Marie Tharp was not permitted to set foot on a research vessel because she was a woman, and women were not allowed on ships. It was that simple and that absolute. She mapped the ocean floor without ever seeing it, without ever being allowed to collect the data herself, or ever standing on the deck of a ship and watching the sonar readings come in. She hadn't felt the roll of the sea beneath her feet as the echo sounder pinged the bottom. The data was collected by men, brought back to shore and handed to her. She turned it into maps. The maps turned into a revolution, and for most of her life, almost no one knew her name. Tonight, we are going to tell Marie Tharp's story, not just the story of her discovery, but the story of the world she worked in, the science she transformed, and the ocean floor she revealed to a civilization that had been sailing over it for thousands of years without knowing what was underneath. It is a story about what happens when the right mind meets the right data at the wrong time, and about what it costs to be right when the people who decide what counts as science have already decided that you are not the right kind of person to do it. It's also a story about patience, the patience of a woman who spent decades drawing a world she was not allowed to visit, and the patience of the data itself, which did not care who was reading it, and which waited quietly on her drafting table until she gave it the shape it had been carrying all along. Marie Tharp drew the bottom of the ocean. The ocean she drew changed everything, and the word they used to dismiss her Girl Talk, became the title of one of the great ironies in the history of science, because the girl talk turned out to be the truth. Marie Tharp was born on July 30th, 1920, in Ypsilanti, Michigan, the only child of Bertha Louise Newton, a German and Latin teacher, and William Edgar Tharp, a soil surveyor for the United States Department of Agriculture. Her father's job required the family to move constantly. William Tharp was sent from state to state, mapping the composition of the soil across the American landscape, and by the time Marie graduated from high school, she had attended roughly 20 different schools in as many towns. It was a rootless childhood, and it might have been a lonely one, but it gave Marie something invaluable: an early, practical education in how to look at the ground and read it. She accompanied her father on his fieldwork, watching him take core samples, draw boundaries on county maps, and translate the invisible composition of the earth, its layers, its textures, its chemistry, into maps that other people could use. She learned that the world has a structure beneath its surface that is not visible to the casual eye, and that the right tools and the right patience can reveal it. She did not know it yet, but she was learning the skill that would define her life, the ability to see what lies beneath a surface that everyone else takes for granted. Despite this early exposure, Marie did not pursue science as a young woman. The field was understood to be men's work, and the career paths available to women in the 1930s and 40s were narrow and clearly marked: teaching, nursing, secretarial work, and a handful of other options that kept women in supporting roles. Marie studied English and music at Ohio University, graduating in 1943 with no particular plan to become a geologist, a cartographer, or anything else related to the earth sciences. She took a drafting course along the way. A practical skill, useful for technical illustration, that would prove more consequential than any other class she attended. But the war changed everything. World War II was pulling millions of men out of universities and workplaces and sending them overseas. And the institutions they left behind were desperate for replacements. For the first time in American history, geology programs began actively recruiting women to fill the empty seats. And Marie, who had taken a geology course in college and found it genuinely interesting, enrolled in an accelerated master's program at the University of Michigan. She earned her master's degree in geology in 1944, one of the few women in her cohort studying a subject that would have been closed to her 2 years earlier. The degree did not open the doors she might have hoped for. She took a job at an oil company in Tulsa, Oklahoma, but found herself confined to an office, collecting maps and organizing data for the men who went into the field. The same division of labor she would encounter again and again throughout her career. The same wall between the woman who processed the data and the men who were allowed to go get it. The pattern was familiar and frustrating. The data was interesting. The work was not. She earned a second degree, this time in mathematics, from the University of Tulsa. And in 1948, she moved to New York City and found a position as a research assistant at the Lamont Geological Observatory, now the Lamont Doherty Earth Observatory, at Columbia University. She was one of the first women hired by the observatory, and her initial duties were clerical: filing, organizing, and drafting, the kind of work that institutions of that era routinely assigned to women, regardless of their qualifications. It was there, in a basement office overlooking the Hudson River, that she met Bruce Charles Heason, a graduate student in geology who was studying the ocean floor. The partnership that followed would last 30 years, produce the most important maps in the history of oceanography, and change the way human beings understand their planet. But in 1948, it was simply a job, a woman with a geology degree and a talent for drafting, assigned to plot data points for a man who was allowed to go to sea and collect them. Before Marie Tharp began her work, the ocean floor was essentially unknown. Scientists knew it was there. Obviously, they knew it was deep, and they had a rough sense of its average depth from scattered sounding measurements taken by naval vessels and cable-laying ships over the previous century. But they had almost no idea what it looked like. The prevailing assumption, shared by most geologists and oceanographers of the early 20th century, was that the seafloor was flat, a monotonous plain of sediment, featureless and geologically inert, the dumping ground for millions of years of organic debris and mineral particles sinking slowly from the surface. It was imagined as the most boring landscape on the planet, a dead zone of mud, unremarkable and unworthy of serious study. There were a few known features. The mid-Atlantic ridge had been detected in the 1870s during the laying of transatlantic telegraph cables, when engineers noticed that the cable had to be played out over what appeared to be a broad rise in the center of the ocean, and scattered soundings had revealed the general outlines of some mountains and trenches. But no one had attempted a systematic, comprehensive map of the ocean floor. No one had tried to draw the whole thing. The technology that made it possible was sonar. A ship equipped with an echo sounder sends a pulse of sound downward toward the seafloor and measures the time it takes for the echo to return. From the return time and the known speed of sound in water, the depth can be calculated with reasonable precision. By the late 1940s, research vessels from Lamont and other institutions were crisscrossing the Atlantic, pinging the seafloor continuously and recording the results on long rolls of paper, thousands and thousands of depth measurements, each one a single point on the invisible landscape below. The data accumulated rapidly, but it was raw, a mountain of numbers without shape, context, or meaning until someone sat down and turned it into a picture. That someone was Marie Tharp. Her job was to take Bruce Heason's sonar data, the depth measurements collected during his expeditions aboard the research vessel Atlantis and other ships, and plot them by hand onto sheets of paper, creating cross-sectional profiles of the ocean floor along each ship's track. She worked with pens and rulers, plotting each depth measurement at the correct position, then connecting the points to create a continuous line that showed the shape of the seafloor from one side of the ocean to the other. The work was painstaking, repetitive, and exacting. A single transatlantic profile might contain thousands of individual measurements, each one requiring accurate plotting, and the profiles themselves were only useful if they were precisely aligned with one another so that the three-dimensional structure of the seafloor could be inferred from the two-dimensional cross-sections. Marie described the ocean floor as a blank canvas to fill with extraordinary possibilities, and she filled it with a meticulousness that would prove essential when the data began to tell a story that no one was expecting to hear. By 1952, Marie had plotted 6 east-to-west profiles across the North Atlantic, some of them stretching more than 3,500 kilometers. When she laid them side by side and compared their shapes, she noticed something. Each profile showed a prominent ridge running down the center of the Atlantic, the Mid-Atlantic Ridge, which had been known in rough outline for decades. But within the ridge, in every single profile, there was a V-shaped indentation, a notch, a valley, running precisely along the center of the ridge like a crack in a spine. It was continuous, it was symmetrical, and it was exactly what you would expect to see if the ocean floor were being pulled apart from the center, new material rising from deep in the earth to fill the gap, pushing the two halves of the ridge away from each other in opposite directions. Marie was looking at a rift valley, and the rift valley was evidence of seafloor spreading. To understand why Marie Tharp's discovery was dismissed, you have to understand the scientific climate in which she made it. In the early 1950s, the theory of continental drift, the idea that the continents move across the Earth's surface over geological time, was not merely unproven, it was actively ridiculed. It was the flat Earth theory of geology, the idea that marked you as someone who did not understand how serious science worked. The theory had been proposed in its modern form by the German meteorologist Alfred Wegener in 1912, based on the obvious jigsaw puzzle fit of the South American and African coastlines, the distribution of identical fossils on continents separated by thousands of miles of ocean, matching geological formations on opposite sides of the Atlantic, and a range of other evidence suggesting the continents had once been joined and had since drifted apart. The evidence was suggestive, but Wegener could not explain the mechanism. He could not describe a force powerful enough to move entire continents across the surface of the Earth. And without a mechanism, the geological establishment rejected his theory. The rejection was not polite. Continental drift was treated as a fringe idea, an embarrassment, the kind of theory that marked its proponent as someone who did not understand how science worked. Prominent geologists mocked it publicly. Textbooks dismissed it in footnotes. Wegener himself was attacked not just on the merits of his evidence, but on the grounds that he was a meteorologist, not a geologist, and therefore unqualified to have opinions about the movement of continents. He died on a meteorological expedition in Greenland in 1930 and did not live to see his theory vindicated. By the 1950s, mentioning continental drift in a serious geological context was roughly equivalent to mentioning astrology at an astronomy conference. It marked you as a crank, it invited ridicule from your colleagues, and it could damage your career in ways that were difficult to recover from. This was the environment in which Marie Tharp sat down at her drafting table and drew a rift valley running down the center of the Mid-Atlantic Ridge. A rift valley that looked unmistakably like the place where two pieces of the Earth's crust were being pulled apart. When she showed the profiles to Bruce Heason, his reaction was immediate and dismissive. It looked too much like continental drift, he said, and he called it girl talk. The phrase was not merely condescending, it was a professional judgment delivered in the language of gender. a way of saying that the observation was not only wrong, but that it was the kind of wrong that a woman would make. An emotional rather than rational interpretation, intuition dressed up as science. Heezen did not look at the data and conclude that Tharp was mistaken on the evidence. He looked at the conclusion and decided that it could not be right, because if it were right, it would support a theory that no respectable geologist believed in. The data was inconvenient, and the person presenting it was easy to dismiss, and so he dismissed both. Marie did not accept the dismissal. She did not argue, she did not protest, and she did not make a scene. She went back to her drafting table and kept working because the Rift Valley was in the data, and the data did not go away because someone called it a name. She later wrote that she thought the Rift Valley was real and kept looking for it in all the data she could get. This quiet stubbornness, the refusal to abandon an observation because a colleague found it uncomfortable, is the quality that separates Marie Tharp from the many other scientists who might have noticed the same pattern and let it go. She did not let it go. She kept plotting. She kept looking. And the Rift Valley kept appearing. Profile after profile, consistent and undeniable. A crack in the center of the ocean that would eventually crack open the foundations of geology itself. The evidence that finally forced Bruce to take Marie seriously did not come from her drafting table. It came from his own research, delivered by an assistant who had no idea what he was about to prove. Heezen had hired a young researcher named Howard Foster to plot the locations of earthquake epicenters in the Atlantic Ocean as part of a separate project studying the relationship between undersea earthquakes and large-scale sediment flows called turbidity currents. The project had nothing to do with Tharp's Rift Valley. It was not designed to test her hypothesis. It was a completely independent investigation using different data, different methods, and different questions. Foster's work produced a map of the Atlantic Ocean, dotted with the locations of every recorded earthquake epicenter, hundreds of them accumulated from decades of seismological records, and when the map was completed, it showed a striking and unmistakable pattern. The earthquakes were not randomly distributed. They were concentrated along a narrow band running precisely down the center of the Atlantic, tracing a line that followed the crest of the Mid-Atlantic Ridge with almost perfect fidelity. When Heezen laid Foster's earthquake map over Tharp's bathymetric profiles, the alignment was unmistakable. The earthquake epicenters fell directly into the Rift Valley that Tharp had identified. The earthquakes were happening exactly where Tharp's data said the ocean floor was being pulled apart. The two data sets, collected independently by different people using different methods for different purposes, were telling the same story. The ocean floor was splitting along the center of the Mid-Atlantic Ridge, and the earthquakes were the sound of it tearing. Heezen could no longer dismiss the Rift Valley as girl talk. The evidence was too strong, the correlation too precise, and the implication too clear. Something was happening at the center of the ocean that the existing models of geology could not explain. Heezen did not immediately embrace continental drift. His initial interpretation was more conservative. He favored a version of the expanding Earth hypothesis, the idea that the Earth itself was growing larger over time, stretching its crust and creating the rift valleys as it expanded. This hypothesis avoided the problem of explaining how continents could plough through solid oceanic crust, but it introduced its own difficulties, and it was eventually abandoned as the evidence for plate tectonics accumulated from multiple independent sources. What mattered in the immediate term was that Heezen accepted the reality of the Rift Valley and agreed to publish the findings. The first physiographic map of the North Atlantic ocean floor, based on Tharp's drafting and Heezen's data, was published in 1957. It showed the ocean floor as no one had ever seen it, a landscape of mountains, valleys, fracture zones, and abyssal plains dominated by the enormous ridge system running down the Atlantic center with its telltale Rift Valley splitting the crest. The map was beautiful, it was revolutionary, and it bore both their names. The publication of the North Atlantic map was a turning point, but the full significance of the Rift Valley would not be recognized for several more years. Through the late 1950s and 60s, as Tharp and Heezen extended their mapping to other oceans, the Rift Valley kept appearing. In the Indian Ocean, in the Pacific, in the Southern Ocean, always at the center of the mid-ocean ridge system, always accompanied by concentrated earthquake activity. The pattern was global. The rift was not a local anomaly. It was a continuous feature running through every ocean on Earth, a 40,000-mile crack in the planet's surface, and it was evidence of a process, seafloor spreading, that would become the foundation of the theory of plate tectonics. Marie Tharp had seen it first. She had seen it in 6 profiles across the North Atlantic, plotted by hand in a basement office, and she had been right. The maps that Marie Tharp and Bruce Heezen produced over the following 2 decades are among the most important scientific documents of the 20th century. Working from an ever-growing body of sonar data collected by research vessels from Lamont, the Woods Hole Oceanographic Institution, the British, French, and Soviet oceanographic programs, and eventually from military sonar data declassified during the Cold War. Tharp drew the ocean floor in a style that had never been attempted before. Physiographic diagrams, 3-dimensional perspective drawings that showed the sea floor as it would appear if the water were drained away. The technique transformed raw depth measurements into a visual landscape that anyone could understand. Mountains that looked like mountains, valleys that looked like valleys, ridges and trenches and fracture zones rendered with an artistic clarity that made the invisible visible. The maps were painted by the Austrian artist Heinrich Beran, who translated Tharp's technical drawings into the vivid, panoramic illustrations that became iconic. The Heezen-Tharp maps, as they were credited with Heezen's name always first, were published in stages: the North Atlantic in 1957, the South Atlantic in 1961, the Indian Ocean in 1964, and finally, in 1977, the complete World Ocean Floor Map, published by the Office of Naval Research. The World Ocean Floor Map is still in use today, still hanging on the walls of oceanography departments and geology classrooms around the world, and it remains one of the most widely reproduced scientific images ever created. It showed, for the first time, the full extent of the mid-ocean ridge system, a continuous mountain range running through every ocean, longer than any mountain chain on land, with the Rift Valley splitting its crest like a zipper being pulled apart. The impact of these maps on the earth sciences cannot be overstated. They provided the visual evidence that made plate tectonics comprehensible to a generation of scientists who had been trained to reject continental drift. When you could see the mid-ocean ridge, when you could see the Rift Valley splitting its crest, when you could see the symmetry of the ocean floor on either side of the ridge, younger crust near the center, progressively older crust toward the margins, the mirror image that proved new rock was being created at the center and pushed outward in both directions. The theory of seafloor spreading became not just plausible, but obvious. The maps did not prove plate tectonics by themselves, but they made the theory visible, and visibility, in science as in everything else, is the difference between an idea that can be argued about and an idea that can be seen. Marie Tharp gave plate tectonics a face, a visible, undeniable, beautiful face, and once you had seen it, you could not unsee it. Throughout this period, Marie Tharp remained in the office. She did not join a research cruise until 1968, 16 years after her discovery of the Rift Valley, and only after the rule barring women from research vessels was finally relaxed. For 2 decades, she had mapped an ocean she had never been allowed to visit, drawing landscapes she had never seen with her own eyes, working from data collected by men who went to sea while she stayed behind. The injustice of this arrangement was not lost on her, but she rarely spoke about it publicly, preferring to let the maps speak for themselves. The maps spoke loudly enough. They said that the ocean floor was not flat. They said that the continents were moving. They said that the Earth was a dynamic, restless, constantly reshaping planet whose surface was being created and destroyed in a cycle that had been running for billions of years. And they said that the person who had first seen the evidence for all of this was a woman who had not been allowed on the boat. The relationship between Marie Tharp and Bruce Heezen was one of the most productive and most complicated collaborations in the history of science. They worked together for nearly 30 years, from the late 1940s until Heezen's death in 1977, producing maps, papers, and scientific contributions that transformed the earth sciences. Their names appeared together on virtually everything they published, though the nature of their respective contributions was not always accurately reflected in the order of the credits. Heezen collected the data. Tharp drew the maps. Heezen presented the findings at conferences. Tharp stayed in the office. Heezen was the public face of the partnership, the one who gave the lectures, accepted the invitations, and received the recognition. Tharp was the engine behind the face, the one whose meticulous draftsmanship and visual genius turned raw numbers into the images that changed the world. The dynamic was shaped by the norms of their era and by the personalities involved. Heezen was ambitious, charismatic, and comfortable in the spotlight, a natural public figure who gave compelling lectures, cultivated relationships with funding agencies, and moved easily through the male-dominated social world of mid-century academic science. He was also, by several accounts, possessive of the work and not always generous in acknowledging Tharp's contributions. A pattern that was not unusual for the time, but that had real consequences for how the history of their partnership was recorded. Marie, by contrast, was quiet, intensely private, and disinclined to fight for credit in a system that was structurally designed to deny it to her. She later described herself as someone who preferred to let the work speak for itself, and for most of her career, the work was attributed primarily to heathen. This was not unusual for the time. Women in mid-century science were routinely undercredited, their contributions absorbed into the reputations of the men they worked with. But it was particularly consequential in Tharp's case, because her contribution was not supplementary, it was foundational. Without her maps, the data was just numbers. Without her eye, the Rift Valley was just a line on a profile. The insight was hers, and the visual language that made the insight communicable was hers, and for most of her life, this was not widely known. The partnership was also marked by genuine conflict. Heathen's initial dismissal of the Rift Valley as girl talk wounded Tharp professionally, and the wound was slow to heal. Even after he accepted the reality of the rift, the dynamic between them remained unequal. He, the principal investigator, she, the technical assistant, regardless of the actual distribution of intellectual labor. In the late 1960s, a dispute with their supervisor at Lamont, Maurice Ewing, led to Heathen's estrangement from the observatory, and Tharp was caught in the middle, forced to continue her work under difficult institutional circumstances. She moved her drafting operation to her home in South Nyack, New York, where she continued to produce maps at the same exacting standard, working from data shipped to her by mail and by courier. On June 21, 1977, Bruce Heathen died of a heart attack aboard the submarine NR-1 while conducting a dive near Iceland to observe the Mid-Atlantic Ridge, the very feature that he and Tharp had spent 3 decades mapping. He was 53 years old. Tharp was devastated. Whatever the complications of their relationship, Heathen had been her partner, her collaborator, and the person whose data had made her maps possible. His death left her alone with the work, and she spent the remaining years of her career completing the comprehensive World Ocean Floor Map, which was published later that year. The map bore both their names, Heathen and Tharp, as it should have, because the work had always belonged to both of them, even when the credit had not. Marie Tharp spent the years after Heathen's death completing their shared work and running a small map distribution business from her home in South Nyack, New York. She retired from Columbia University in 1982, and for more than a decade after that, she lived quietly, largely unknown to the general public and under-recognized even within the scientific community that her maps had transformed. The maps hung on walls in every oceanography department in the world. The theory they had helped prove was taught in every introductory Earth science course on the planet. Plate tectonics had become the foundation of modern geology, the unifying framework that explains earthquakes, volcanoes, mountain building, and the distribution of life on Earth. But the woman who had first seen the evidence for it in 6 sonar profiles across the North Atlantic was not a household name. She was not even a classroom name. Students learned about Alfred Wegener and his theory of continental drift. They learned about Harry Hess and his theory of seafloor spreading. They learned about J. Tuzo Wilson and his theory of transform faults. They did not learn about Marie Tharp, the woman who drew the map that made all of it visible. The recognition, when it finally came, arrived in a quiet rush near the end of her life. In 1997, the Library of Congress named her one of the 4 greatest cartographers of the 20th century. In 1999, the Woods Hole Oceanographic Institution awarded her the Mary Sears Woman Pioneer in Oceanography Award. In 2001, she received the first Lamont Doherty Heritage Award from the observatory where she had spent most of her career working in the shadows. These honours were deserved and they were appreciated, but they came decades after the work that earned them, and they came to a woman who was in her late 70s and 80s, her health declining, her most productive years long behind her. The timing of recognition matters. Being honoured at 80 for work you did at 32 is not the same as being honoured at 32. The honour says you were right. The delay says the world was not ready to admit it. Marie Tharp died of cancer on August 23, 2006, at the age of 86. In the years since her death, her reputation has grown steadily, fueled by a biography, a children's book, a Google Doodle, and a growing awareness within the scientific community and the general public that her contribution to the earth sciences was not supplementary but essential. In 2023, the United States Navy announced the renaming of a ship in her honour, the USNS Marie Tharp, a survey vessel, appropriately enough, designed to map the ocean floor. The Library of Congress holds her papers, her maps, her correspondence, and her research notes, the largest manuscript collection in the Geography and Map Division, a testament to the scale of what she accomplished and to the care with which she documented it. The ocean floor that Marie Tharp mapped is still being mapped today, with satellite altimetry, multi-beam sonar, and autonomous underwater vehicles that can survey the seabed with a precision she could not have imagined. Her maps have been refined, corrected, and superseded in their details by technology that is vastly more powerful than the echo sounders and the pens and rulers she worked with. But the fundamental picture she drew, the mid-ocean ridges, the rift valleys, the fracture zones, the abyssal plains, the dynamic and restless landscape beneath the waves, has not changed. She got it right. She got it right with primitive tools in a basement office while being told that she was wrong, and while being excluded from the ships that collected the data she needed, and while working in a field that did not believe women belonged in it. She got it right, and the world she revealed is the world we still live on. If you could drain the oceans, pull the plug, and let the water flow away, leaving the seafloor exposed to the sun for the first time in 4 billion years, you would see the world that Marie Tharp drew. It would not look like what you expect. It would not look like the bottom of a swimming pool, flat, featureless, covered in a thin layer of muck. It would look like a planet, a wild, dramatic, mountainous planet with ranges taller and longer than any on land, with trenches so deep that the tallest buildings on Earth would disappear inside them without a trace, with volcanic ridges pouring fresh rock into cracks that run for thousands of miles, and with vast flat plains of sediment interrupted by isolated seamounts rising kilometres above the surrounding floor. Each one a world unto itself, colonised by organisms found nowhere else on Earth, each one a mountain that no human eye has ever seen from the outside. The mid-ocean ridge system that Marie Tharp first identified in her North Atlantic profiles is the largest geological feature on the planet, the single biggest thing on Earth, and one of the least known. It stretches roughly 65,000 kilometers through every ocean on Earth, longer than the combined length of every mountain range on every continent. It rises, on average, 2 to 3 kilometers above the surrounding abyssal plains, and its crest is split by the rift valley that Tharp discovered, the crack where new oceanic crust is born from magma rising from the Earth's mantle. The ridge is not a static structure. It is not a monument or a ruin. It is a living seam, a place where the planet is continuously creating itself, pushing fresh rock outward at a rate of a few centimeters per year, building new ocean floor that will eventually travel thousands of kilometers across the seabed before being swallowed back into the mantle at a deep ocean trench and recycled into the interior of the planet. This process, seafloor spreading, is the mechanism that drives plate tectonics, the engine that moves continents, builds mountains, triggers earthquakes, opens and closes oceans, and reshapes the surface of the planet on timescales of millions of years. It is the mechanism that Alfred Wegener could not identify when he proposed continental drift in 1912. And its discovery, driven in large part by Tharp's mapping of the Rift Valley, was the missing piece that transformed continental drift from an elegant hypothesis into a proven theory. The continents are not ploughing through the ocean floor as Wegener had imagined. They are riding on it, carried along by the conveyor belt of new crust being created at the ridges and destroyed at the trenches, passengers on a planetary system that has been running for billions of years and that will continue running for billions more long after every city and every civilization has been forgotten. Marie Tharp did not discover plate tectonics. No single person did. It was a collective achievement built from the work of hundreds of scientists across decades: geophysicists, seismologists, paleontologists, oceanographers, each one contributing a piece of the puzzle. But Marie Tharp provided the image, the picture, the map, the visual proof that made the theory real to the human eye and real to the human mind. Before her maps, the ocean floor was invisible, a blank space on the globe, a mystery that scientists could theorize about but could not see. After her maps, it was a landscape, a world, a place with features you could name and point to and argue about and eventually understand. She made the invisible visible, and in doing so, she changed what it meant to understand the Earth. She did it from a basement office. She did it by hand, with ink that smudged and rulers that slipped and paper that tore if she pressed too hard. She did it while being told that her best idea was girl talk. And the girl talk turned out to be the map of the world. Marie Tharp drew the bottom of the ocean with pens and rulers, sitting at a drafting table in a room she was not allowed to leave, working from data she was not allowed to collect, and she got it right. The Rift Valley she discovered in 1952, the crack in the spine of the Mid-Atlantic Ridge that her colleague dismissed as girl talk, turned out to be the most important geological feature anyone had identified in the 20th century. It proved that the ocean floor is spreading. It proved that the continents are moving. It proved that the Earth is alive, restless, continuously remaking itself from the inside out. She was not allowed on the ships, nor to collect the data. She was not allowed to present the findings. She was called a name that was meant to make her stop. But she didn't. She kept plotting, drawing, and looking for the rift in every profile that crossed her desk, because the data was the data and it didn't care who was reading it. Sleep well tonight. The ocean floor is still there, still spreading, still splitting along the line that Marie Tharp drew by hand more than 70 years ago. She got it right. The world just took a while to notice. Thank you for listening.